Here's lesson 6, combinations. So we're going to do something similar to our permutations, but modify it a little bit here. So from a group of 4 students, 3 are to be elected for an executive committee with specific positions. This part's key. So first position is president, second position is vice president, and third position is treasurer. Does the order in which the students are elected matter? Yeah, it does. Roles would be different. Okay, so if I draw your name first and you're president, that's a big difference than if I drew your name third and you became treasurer. You have a different role. In how many ways can the positions be filled? So if we have 4 kids, we've got 3 positions. So you've got 4 choices, and then 3 choices, and then 2 choices. So 24 different ways that we can make this committee. Now we're going to change the scenario a little bit. We're just selecting 3 students from the 4 to be on the swim team. Is the order still important now? Is there a specific role that they get when they're on the swim team? If the answer is no, it does not matter who is chosen first. So if I select your name first and you're on the swim team versus whether I select your name third, you're still on the swim team. You still have the same role. How many possible committees can there be from these 4 students? So before we used NPR, this time we're going to use, it looks very similar, but it's going to be a combination. It's 4C3. And if we draw this out, we've got 4 students, A, B, C, and D, and let's make all the possible combinations of letters here. 3 letters, we're choosing 3. So A, B, C, and we've got A, B, D, we've got A, C, D, and we've got B, C, D. All right, those are all the same. Now in this scenario, C, D, B is the same. It's the same swim team. We're just writing the kids' names in different order. So they're not distinct, they're not unique. So we're not going to double it up. So there's only 4 ways to do that. So on your calculators, if you go to math, you go to probability, and there it is, number 3, NCR. And we're doing 4, and we're choosing 3. So there's only 4 combinations. So this part's key. If the order matters or the order makes a difference, you're dealing with a permutation. If the order does not matter, makes no difference, that's a combination problem. So let's do a couple examples here. How many, let's get rid of this. How many different 5-card poker hands are possible? That is a combination. Okay, the order doesn't matter. If you've got ace, king, queen, jack, and 10, that's the same hand as if you have 10, jack, ace, queen, king. All right, it's the same hand. It has the same value. So that would be a combination. How many different 3-letter words can you make using 3 letters from the word triangle? That's a permutation. When you're reading words, ABC is different than BAC, okay? Those are different words, as it were. So that is a permutation. A pizza parlor offers 25 different toppings. How many different pizzas with 4 toppings are possible? That's a combination. Okay, whether you ask for pepperoni and mushrooms or mushrooms and pepperonis, you're still going to get them on your pizza. So it's a combination. How many arrangements can 6 people stand in a row? That's a permutation. All right, if person A is on one side of the photo, person B is on the other, versus person B on one side of the photo and person A on the right side, those are different pictures. You're going to get different things. So the formula for combinations is as follows. And in previous lessons, we used a similar thing for permutations. I showed you where to find the NCR in your calculator. Let's pull that up again. So you would go to math, you would go over to probability, and go down to NCR. Okay. All right, 3 students from a class of 10 are chosen to go on a school trip. How many ways can they be selected? So 10C3, and that's going to give you 120 different combos. Group of 5 students are selected from a class of 35, so 35C5, and that equals 324,632 ways. Melissa, Brittany, and Sydney, how many of the possible groups include all 3 of these students? Well, if they have to be included, they're out of, we're picking 3 from 3. So there's only one way to do that. And we need to multiply that by the number of ways to select 2 from 32. We still need to make a group of 5. We've already got 3 of them. So we only need to select 2 more. So if we do this, you get 496 different groups. The athletic council decides to form a subcommittee, and there's 15 council members, 9 males and 6 females. The subcommittee must consist of exactly 3 females. Okay, so how do we go about doing this? So if we are selecting a subcommittee of 7 people in total, the first way we're going to have 3 females and 4 males. Okay, so there's 6 females to choose from. So the first part is 6C3, and then there is 9 males to choose from, so 9C4, and we need to multiply these 2. How many ways can the subcommittee be chosen if Bruce must be included? All right, so Bruce is already part of it. So we're down to 6. We're choosing 6, okay, because Bruce is already part of it. And we need to have 3 females. So Bruce, 3 females, and 3 males. So Bruce is already part of it. Okay, we're going to multiply by 6C3 for the females. We're going to multiply by 8C3 for the males. And there's 1120 different subcommittees. From a standard deck of playing cards, how many different sets of cards can be formed? 5 card hands, so there's 52 cards, and we're choosing 5. So 2,598,960. 5 card red hands, so we're picking from the red cards, so there's 26 red cards, we're choosing 5. So there's 65,780 different hands. 5 card hands with exactly 3 black cards. So we're choosing 3 from the black. That means we're choosing 2 from the reds. So there's 845,000 different hands. 5 card hands with at least, this is different than exactly 3 black cards. So there's different combos. There's 3 black, 2 red. There's 4 black, 2 red, and then there's 5 black. Okay, and we need to add up the different scenarios. So the first one, 3 black, 2 red, we got 26, choose 3, multiplied by 26, choose 2. We're going to add that to 26, choose 4, multiplied by 26C1. And we're going to add that to 26C5. And in total, if you do that, you get 1,299,480 different 5 card hands with at least 3 black cards. So from a group of 15 students, a committee of 5 students is needed. So there's no restrictions. So we're just going to use the 15 kids, and we're picking 5 of them. So there's 3,003 different committees, possible committees. If it must consist of exactly 2 males and 3 females, so there's 9 males, so we're choosing 2 of them. And we're multiplying that by choosing 3 from the 6 females. So there's 720 different ways. And the committee must consist of all females. Well, we're choosing 5 from the 6. So there's 6 different committees. And must include at least 1 male. Okay, so we can have 1 male, 4 female, 2 males, 3 females. We can have 3 males, 2 females, and we can have 4 males, 1 female. Yikes. And we can have 5 males. So first scenario, 1 male. So from 9 we're picking 1. And then from 6 females we're choosing 4. Okay. And we're going to add that to the second scenario. So from 9 males we're choosing 2. And multiply that from 6 females we're choosing 3. And then we're going to add this to our next scenario, which is from 9 males we're choosing 3. And from 6 females we're choosing 2. And our fourth scenario, from 9 males we're choosing 4, multiplied by choosing 1 female from 6. And our last scenario, we are choosing 5 from the 9 males. Okay, so that gives us 2,997 ways. Now there is another way to kind of think about this problem. If we figure out the total number of combos and we subtract the number that are just all female, you get actually the same answer. All right, equivalent combinations. So Jane calculated 10C2 to be 45. She then calculated 10C8 to be 45. Why are they equivalent? Well, if you can picture 10 people, how many is it? 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 9. One more. Okay. All right, so we've got 10 people and we're choosing 2. Okay, so maybe this round I pick 2. All right, well notice that there's 8 left over. And maybe I choose these 2, but hold on, there's still 8 left over. And maybe I'm choosing those 2, but hold on, there's still 8 left over. And maybe I choose those 2, and hold on, there's still 8 left over. Oops. And maybe I choose this one and that one, but there's still, guess what, 8 left over. So when you are choosing 2 from 10, you're actually also choosing 8. It's like the converse, all right? There has to be 8 left over. So in this case, when you split 10 people into groups of 2, you are also splitting them into a group of 8, the remaining people. So it's equivalent. So this would be equivalent to 24C9. Solving for n in combination problems. So we didn't get to this one in class, so I'm going to do this on Monday. During a Pee Wee hockey tryout, we did do this one, but we didn't do the polygons and diagonals. All right, so in the Pee Wee hockey tryout, all of the players met on the ice and they shook hands. So there were 300 handshakes. Now, when you are doing a handshake, 2 people need to meet. And it doesn't matter if person 1 shake hands with person 2 or person 2 shake hands with person 1, it's still the same handshake. Okay, so this is a combination problem. And we need to use the formula that was written down before. Okay, so NC2 equals 300. And if we expand this, we have n factorial over 2 factorial n minus 2 factorial, and that equals 300. So let's expand the top part, n minus 1, n minus 2 factorial over top of 2 factorial n minus 2 factorial. That equals 300. And you'll notice that the n minus 2 cancels out. So we're left with n, and I'm going to do a little extra step here. So n squared minus n over 2 is equal to 300. 2 factorial is the same as 2. And then let's multiply by 2. And we'll get n squared minus n is equal to 600. And if we subtract 600 from each side, we end up at n squared minus n minus 600 equals 0. Now we can factor this, and if you factor it, you get n minus 25, n plus 24 equals 0. So our solutions are n equals 25 or n equals negative 24. Well, we can't have a negative factorial if you were to put negative 24 factorial in there. So we must eliminate that answer and be left with, there must be 25 kids. And here's this last problem that we didn't do in class, so we'll do Monday, but I'll include it on this video. So the number of diagonals in a regular n-sided polygon is nc2 minus n. How many diagonals are there in a regular octagon? What do we know about octagons? Octagons is 8 sides. So n equals 8. So really we're doing 8c2 minus 8. And if you do that, you get 20 ways. Or sorry, 20 diagonals. A polygon has 65 diagonals. So in this case, we know the diagonals, we don't know the number of sides. So we use the same formula that was given to us up here, and we're going to set it equal to 65. All right, let's expand the nc2 part. So n factorial over 2 factorial, n minus 2 factorial minus n, and that equals 65. We end up with the same thing as the last example, where we have n minus 1, n minus 2 factorial over top of 2, n minus 2 factorial, minus n equals 65. That simplifies again. And then we're going to be left with n minus 1 over top of 2 minus n equals 65. And let's do some rearranging here. Okay? So if we multiply everything by 2, we will get, that part simplifies, so we're left with n minus 1 on top, minus 2n is equal to 130. And let's expand, so n squared minus n minus 2n is equal to 130. Combine some like terms here. Bring the 130 over. And then we got a factor, n minus 13, n plus 10. So our solutions are n equals 13 and n equals negative 10. We can't have a negative factorial, so there must be a 13-sided polygon. And if any of you know what a 13-sided polygon is, the name of it, bonus marks for you.